Hey everyone, Mr. Smith here. Excited to start a new unit on uniform circular motion and gravitation and celestial mechanics. Should be a lot of fun. To start off, we're going to talk about uniform circular motion. So this is kind of like motion in 2 dimensions. But as I've mentioned earlier, I do like, because there's so much we can do with it and it ties into gravitation so well, I do like to kind of separate this out. So in this video lesson, we're going to talk about uniform circular motion. So what is it? What are the equations governing uniform circular motion? And then do a few examples together. So let's get started. So what is uniform circular motion? It is motion that occurs when an object is moving in a circle with a constant speed and a constant radius. So that is those are the 2 important things. So constant speed and constant radius. Now, just as an aside, you don't necessarily have to copy this down right now, but for things like, let me just use here's the Earth, and for things like maybe some kind of satellite orbiting the Earth, that's just constantly going around and around and around. And later on, we might analyze these situations, even though their paths might not be perfectly circular, they're actually ellipses. They're close enough to circles that we'll be able to analyze them using uniform circular motion. That's like, that is an example of something just going around and around and around and around and around. And there's, countless other things too, like, maybe twirling a ball, like just around and around and around your head or something like that. But there's situations too, like say maybe a bird swooping in on a dive, or a plane kind of swooping in. I may regret this, but that looks like a person. Oh, okay, that's a plane, whatever. But like a plane coming in and coming out of a dive, they might not be doing a loop-to-loop, but we can, if parts of their motion kind of represent like the arc or like just a part of a circle, we can actually apply uniform circular motion to situations like these. Even later on, we'll do a car doing a loop-to-loop around like a vertical loop, and roller coasters and stuff like that. So, even though, like, this is what I'm trying to say is we can use uniform circular motion to analyze motion that's circular or nearly circular, but also for things where, it's just the motion is like just kind of like part of a circle. But the big idea is it's constant speed and constant radius. So here's a little visual. And so if you can imagine a stopper on a string just being spun in a vertical plane, kind of like that. The speed as you twirl it around and around and around remains constant, and so does the radius. However, because the direction of the stopper is changing, the velocity is changing. And so what this diagram illustrates is that the velocity vector is always tangent to the circle. So you can see if the radius is pointing out here, at this point, the stopper would be kind of moving kind of up and to the left. But at this point here, the velocity or the stopper would instantaneously be moving kind of down and to the left. And it's always tangent to the circle. And the consequence of this is that even though the speed is constant, but because the velocity vector is changing direction, we have acceleration occurring. So remember, acceleration is a change in velocity over change in time, and the velocity is changing. The speed isn't, but the direction is. The velocity is changing, so it is accelerating. And acceleration, and what we call the centripetal acceleration. So I think I make this definition later on, but this idea of centripetal is, you might have heard that word before too. It means center seeking. So the acceleration is actually directed towards the center of the circle. So we're going to actually show that as right now. So right now we've established, velocity is changing, speed isn't, but direction is. So velocity is changing and acceleration is happening. So we want to answer two things. So if there is acceleration, what's the direction? And what's the magnitude of that acceleration? So we're going to find that out right now. So you guys have some kind of similar diagram on your lesson sheet. So imagine we have an object moving around this circle in uniform circular motion. And so I've kind of got like three kind of like snapshots in time. So I want you to consider like an initial velocity here and a final velocity here. And then later on, we're going to consider an initial velocity and final velocity where they're kind of closer together. And then finally, an initial velocity and a final velocity where those are pretty close together. I mentioned that we can show the direction is towards the center of the circle using the fact that acceleration equals change of velocity over time. So what are the directions of that change of velocity? So I think I have a line tool. Do I have a line tool? If not, I'll be arrow options. Probably something good to figure out beforehand. I think I'm going to be freestyling. Highlighter, yeah. All right, guys. I'm going to be freestyling some lines here, so I'm going to do my best. So we're going to draw a delta V for these different situations. V2 minus V1. So here's V2. And from there, I'm going to draw minus V1. I'm just being very careful. That looks pretty good. You at home, you can use a ruler. But there's minus V1. And so delta V would be something like so. The V2 and V1 are kind of far apart. And again, the acceleration is in the same direction as the change of velocity, because acceleration is change of velocity over change in time, and change in time is just a scalar. So let's try that at another spot. So here I have V1 going down, V2 a little bit later on. If I draw V2 minus V1 here, just be careful, that's not awful. There's minus V1. And then delta V would be something like so. And finally, if I try it one more time, so here's V1 to the right, here's V2. If I draw minus V1, I get something like that. And then check this out. The change in velocity vector, and hopefully you're convinced, that change in velocity vector, it certainly looks, this isn't a proof for sure, but it certainly looks like that change in velocity vector as we make those 2 points closer and closer together, that that change in velocity vector is pointing towards the center of the circle. And so the acceleration is pointing towards the center of the circle as well. So I might just add a little blurb with that. So since the acceleration, and I'm going to use, since the acceleration is the limit, so like the instantaneous acceleration is the limit as delta t approaches 0. So you're making that time closer and closer together, and you're making these points closer and closer together of delta v over delta t. So we can see as we shrink that delta t, delta v goes towards the center of the circle. And delta v points to the center. The acceleration points to the center as well. So I wanted to do that with you guys just to kind of actually, not instead of to say, hey, just take my word for it. Here's a little visual exercise we can do to kind of convince ourselves that, yeah, the acceleration is happening and it actually goes towards the center of the circle, uniform circular motion. So that's really cool. Something else about the motion. Now that we've established that the acceleration, and we often call the acceleration AC, force centripetal acceleration. The instantaneous velocity is always tangent to the circle, but the acceleration is always towards the center of the circle. So these two things are always perpendicular to each other. That's just by definition. Towards the center and tangent always makes, on a circle, always makes a right angle. So just keep that in mind. What about the magnitude? I could just give you, say, hey, here's the formula for the magnitude, but it's something that we can derive, and it's not an easy derivation, but it's it's not terribly awful as well. So I like to do it with my students. So let's do it. So imagine, excuse me, imagine that we have some circular motion. And so imagine that the motion kind of looks like this. And so here is the center of a circle. And so initially we're at some position R1, then we move along the circle a little bit, and now we're at some position R2. And the motion is kind of that way. And we'll call the angle between the position 1 and position 2, we'll call that theta. If we draw the change in position vector from R2, we draw negative R1. Because of a Z pattern, like in our grade 9 math course, that angle would be theta as well. And we have this little triangle. In this triangle, we have this radius again, and this angle theta in between. If we think about the same motion, excuse me, the same motion and the what the velocity vector would look like. So at R1, the velocity vector would be tangent pointing off this way, V1. At R2, it's pointing off this way, V2, like so. But the angle between V1 and V2, if you put them tail to tail, is actually the same as the angle between R1 and R2. And if we draw, we can make a little triangle. If we draw V2 and then minus V1, we get that same angle, the Z pattern. And then V2 minus V1, that just gives us the change in velocity. And what you have is two similar triangles. Triangles that have the same shape, not necessarily the same size, which means, and this is our starting point for the derivation. If you take the change in velocity and divide by the speed, V, it's the same as the change in radius, the size of it, divided by R. Now here, I've just let the size of R1 equal the size of R2. I'm just calling that R because it's uniform circular motion. So that position vector is always going to be R units long because we're going in a circle. And also, V1 and V2, the size of those vectors, that's just V, right? Because uniform circular motion, you have the same speed, which we're going to call V. If we do some rearranging here, we get the size of V, delta V, equals V times delta R, the size of delta R, over R. And so keep that in mind. Now let's talk about the centripetal acceleration. We want to get an expression for that. So the centripetal acceleration is the limit, we talked about this earlier, as delta t approaches 0 of the change in velocity over change in time. So this is the magnitude of the centripetal acceleration. So we have the magnitude of the velocity. So let's just remember that circle. That just means you put the points closer and closer together. Those 2 points connected by some delta t, just shrink the time interval down by a lot. Well, we have an expression for delta v here, right? That's equal to the limit as delta t approaches 0. And I'm going to plug in what delta v is equal to. It's equal to v times delta r. And on the bottom, I'll have my r and then times delta t. So you can see I still have my delta t. I just plugged in for delta v. I've got v delta r over r, v delta r over r, delta t still on the bottom. I can actually play around this a bit because, and for those of you who have taken calculus, this will make sense to you, but it should make sense for all of us as well. But v and r, those are constant. Those aren't changing. So I can actually pull them outside like this. So v over r times the limit as delta t approaches 0 of delta r over delta t. So guys, delta r over delta t, that's displacement over time. That's velocity. And as you take the time being closer and closer to 0, that's giving you the instantaneous velocity. And because we're taking the magnitude of the position, the change of position, what we're getting is this expression here. The limit is delta t approaches 0 of delta r over delta t, the magnitude, is exactly the instantaneous speed. All of this is actually equal just to the instantaneous speed, which is v. It's uniform circular motion, the same speed. So this is really, really cool, guys. The centripetal acceleration is v squared over r. So this is what we've just shown here. We've shown that the magnitude of the centripetal acceleration is centripetal acceleration, AC, equals v squared over r. And we can do a little dimensional analysis here. Just to make sure, if you want to see that the units match up. So since we have v squared over r, and I'm just looking at this in terms of units. So the units of v squared are meters squared per second squared. And the units of r are meters. So what we have is we have meters on the bottom and a factor of meters in the top of this expression on the top. One of them divides out. And look what you're left with. You're left with meters per second squared. So the units do match up. So now we've actually kind of quantified. We've said, okay, acceleration is happening. We now know the direction to the center of the circle, always towards the center. And we have the size of the centripetal acceleration. It's given by v squared over r. That's pretty cool. We're going to make a connection here between the speed of an object in circular motion and frequency and period. So if you recall from your grade 11 course, the period, and you traditionally did this in your unit on waves, but period is just basically the time for one revolution. And that's in seconds. The frequency is the number of revolutions per second. So the units for that is, since it's per second, it's like 1 over seconds or inverse seconds, or there's a unit for that you might have seen in your grade 11 course called the hertz. So often you'll have the frequency in hertz. And the relationship between frequency and period is they're just reciprocals of each other, which makes sense. So here's what I mean by that. Let's say you have a frequency of 2 hertz. So this means you're doing 2 revolutions every second. Well, what's the period then? Well, if you're doing 2 revolutions every second, then every revolution should be half a second or 0.5 seconds. So there's this relationship. Period and frequency are just reciprocals of each other. And frequency is 1 over the period, works both ways. So we can connect the speed of uniform circular motion with the frequency and period this way. Remember, guys, speed is just distance over time. And think about uniform circular motion. As an object goes around the entire circle, what distance does it travel? Well, it travels the circumference of the circle, right? Which is just, I think I added an extra letter in there, that's okay. Which is just the circumference of the circle. And the time it takes to do one motion around the circle is the period, t. And so you have this thing that relates speed, radius, and period, and it's just distance over time, 2 pi r over t. And if you replace 1 over t with the frequency, you get an equivalent expression, 2 pi rf. So when we do uniform circular motion problems, sometimes we'll know the speed. In fact, most of the time, you won't know the speed. What you'll know is the period. And sometimes you'll know the frequency as well. For example, if you consider the Earth going around the sun, I bet none of you guys could tell me how fast the Earth is moving around the sun. But I bet everybody could tell me what the period is, how long it takes the Earth to move around the sun. It takes a year, 365 days, right? So there's a lot of scenarios where we know the period instead of V. And so these will be useful for us. And if you do if you take our expressions for V, being 2 pi r over t or 2 pi r f, if you just plug those into v squared over r, you get 3 different ways to calculate centripetal acceleration. These 3 formulas are the same formula, just with different variables. So if you have this tangential speed, you can use this one. If you have the period, this gives you the centripetal acceleration. If you're given the frequency, this one gives you the centripetal acceleration. So now that we've set all that up, objects in uniform circular motion are accelerating. The acceleration is towards the center of the circle, and its magnitude is v squared over r. Let's do some examples. So I think everybody has some experience on a merry-go-round. So this child is on a merry-go-round. That's 4. The child is on a horse 4.4 meters from the center. And I think we all understand that even though sometimes the horses bob up and down, we're going to just assume they're going in a perfect circle. And the child does 3 revolutions of the ride every single minute. We're going to find the magnitude of the child's centripetal acceleration. So to do that, we have to think, which formula are we going to use here? Which piece of information, V, T, or F, can we get from the problem? So the key is we're going to use this information here. 3 complete revolutions every single minute. So it's obviously not a speed. Now, for some of you, you may be able to pick off the period. If there's 3 revolutions per minute or 60 seconds, then that means that 1 revolution is in 20 seconds. So the period here, 20 seconds. It takes 20 seconds to do 1 full revolution. And we are given the radius, 4.4 meters. And so we're ready to find the centripetal acceleration. That's what we're trying to find. So let's do it. So the formula we're using is 4 pi squared r over t squared. Let's plug those in. I personally, at this here, use my pi button because I know it's exact. We'll plug in 4.4, and our period is 20, and we'll work that out. So I use my pi button. If you use 3.14, like, we're all going to get close to the same answer. It's not a big deal. So 4 times pi squared times 4.4 divided by 20. So about 8.7 meters per second squared. So pretty fun. You know, it's enough of a, well, I think I forgot to, yeah, you know what? If you're screaming at I was thinking that was a bit high. That counts as my first error for today. I forgot to square my 20. So let's fix that up. Let me retry that, because I was thinking that seems pretty high. That's, for a little kid, that's kind of an intense acceleration to feel. So let me just double check that by 400. Okay, so I think that's a bit better. Yeah, 0.43 meters per second squared. Yeah, I think I'd be a little hesitant putting my 3-year-old on a ride with that high of an acceleration. They're probably going to fly off the ride. But yeah, so that's just a bit of experience calculating a period and using our formulas. That's what we're trying to do here. It's just kind of build up a comfort level with these new formulas. Let's look at our second example. So maybe you've seen one of these. Maybe you have one in your kitchen, a salad spinner. I personally like the lettuce in the bag. It's usually pretty clean. Like, I'll maybe give it a rinse, but like my wife, she's pretty anal about this stuff. She's got to put the lettuce in the salad spinner and pump the salad spinner. So it pumps the button and the spinner spins around really fast. and all the water kind of flies off the lettuce to the outside, and you take it out and you're left with dry lettuce. But you can only put a bit in at a time. But anyway, my wife uses a salad spinner all the time, but it's pretty crazy. Like these small spinners, it can be spinning around very, very fast. And so here at our spinner has a diameter of 19.4 centimeters. So before we do anything, just keep in mind our equations for uniform circular motion involve the radius. So we want to take half of the diameter. So that's 9.7 centimeters for the diameter of our salad spinner. And it's spinning at a really crazy frequency, 780 revolutions per minute. So in this case, what we're going to do is we're going to find the magnitude and direction of this piece of lettuce. So in the question here, from a top-down perspective, at the instant of inspection, the lettuce is moving eastward. So north is that way, east is this way to the right. We're looking top-down. So question to you guys before we even begin doing any calculations is, if that's the way the lettuce is moving at that time, and it's moving clockwise, geez Louise, I think I need to take a break. This is my 4th video shot this morning. It's moving clockwise, which means it's at the top moving east. So if this is a position of a piece of lettuce moving east, what direction is the acceleration in terms of what compass direction is it? So I'll let you think about that for a second. You can pause the video, consult back to what we have about the direction of the acceleration, and unpause when you're ready. But if you're ready for the answer here, the acceleration is always towards the center of the circle. So the acceleration will be south. So what is the magnitude of the centripetal acceleration? So we got r, and we're given information about the frequency, but the units are revolutions per minute. So the frequency is 780 RPMs, revolutions per minute. Now, if we divide that by 60, that will give us the revolutions per second. So that's 13 revolutions per second. And revolutions per second, that's just the unit of hertz. So we had to do a bit of work to get the frequency, 13 hertz. And we're given the radius of our circular motion is 9.7 centimeters. In terms of meters, that's 0.097 meters. And now we're ready to go. We can calculate the centripetal acceleration using the appropriate formula. And this one would be 4 pi squared r f squared. Just consult that I have the right one. Yep, 4 pi squared r f squared. This time I won't forget to square it. So 0.097 times 13 squared. So let's check out the acceleration of this guy. 4 times pi squared. So what we're expecting to get an extremely high acceleration here. Times 0.097 times 13 squared. That's pretty crazy. 647 meters per second squared. And we can finish this problem off by saying the centripetal acceleration is 647 meters per second squared, and the direction is south at the point we're inspecting it. So that's pretty cool. Now, for you or I to experience this acceleration, which is how many times bigger than gravity? But 66 times bigger than gravity, 66 Gs, like we would die. However, this is just a tiny piece of lettuce. So for a tiny piece of lettuce with such a large acceleration, because the mass is so small, the actual force on the lettuce is pretty small too. So your lettuce isn't going to fly off and disintegrate because of all the tremendous forces on it, because its mass is small. But for us, force equals mass and acceleration. For a bigger mass, for like a human, now you're talking very large forces that would crush us and damage us. So pretty interesting example there. Let's do, we're just doing one more example. So most people have these. I kind of have one on behind me because it's kind of hot, but we have a fan. So here we have and we're just playing around with the equations a bit at this point. So we're going to try to find the frequency and period of rotation of a fan. If a spot at the end of one fan blade, that's 15 centimeters from the center, has an acceleration of 2,370 meters per second squared. So we're given the radius, and we just got to make sure we put that into meters. So that's 0.15 meters. Here we have the centripetal acceleration. And in this case, we're asked for the frequency and period. So it really doesn't matter which one we find first. Let's find the frequency first. So we'll be using AC equals 4 pi squared r f squared. Now, when we do celestial mechanics and look at satellites, we'll be doing a lot of rearranging. So it's a good exercise to do it now. To get f by itself, we're dividing AC by all this other stuff, 4 pi squared r. But that only gives you f squared. To get f, we would have to square root everything. And now we can just calculate that. So 2370 divided by 4 pi squared times 0.15. So 2370 divided by 4 divided by pi squared divided by 0.15 and square root. So you get pretty near 20 hertz or 20 revolutions every second. So what's the period? Well, the period and the frequency are reciprocals, 1 divided by each other. So the period would be 1 divided by 20, or 0.05 seconds for 1 revolution. All right. So what do you guys need to know? We now know what uniform circular motion is. Motion in a circle, constant radius, constant speed. Despite constant speed, we know acceleration is occurring because the direction is changing. And that acceleration is always towards the center of the circle. And the governing equations for that acceleration are what's on the screen here. Given the speed, period, or frequency, we should be able to find centripetal acceleration. So what's next? Now that we've talked about uniform circular motion, we can now look at dynamics problems involving things like spinning something around in a circle, or a car driving along a banked road, or a car going in a vertical loop-to-loop. It should be a lot of fun. So until then, hope you guys are staying well. Have a great day, and we'll see you soon.